Yeah, thanks for the introduction, and thank you very much for organizers for having me in a very nice conference and program. I really enjoyed. So today I'll be going to talk about the microscopic description of the truth anomalies of the symmetries and the related with the statistics of braiding of the excitations in the microscopic quantum many-body systems. And my talk will be based on the recent collaboration with fascinating people in Beijing. Yuan is faculty in Peking University, and Han Yu and Yu Yan are both brilliant students in the Peking University. Han Yu is undergrad, who is hopefully moving to the MIT this year. And the Poshen is one of the audience, I'll be also talking about mentioning the upcoming paper with Poshen Abhinav, which is going to appear very soon, hopefully. So, okay, let's get it started. So the playground of my talk will be the topologically ordered phases, which is mostly the gapped phases of matter with the quasi-particle or more generally extended excitations, which are all regarded as the end of the topological operators, which generate the symmetry of the systems. And we are all interested in the universal properties of the global symmetries, such as truth anomalies. In these topological order phases, truth anomalies of the symmetry is very important. For instance, it is directly associated with braiding and statistics of anyons or extended excitations. And for instance, if you have anyons, which is not bosons, which carry the fractional statistics, then it implies that we cannot basically condense anyons. In other words, we cannot gauge this higher form symmetry generated by topological operators, and basically the fractional statistics prohibits trivial gap phases. And this is regarded as a dynamical consequence. This obstruction to trivial gap phase is regarded as a dynamical consequence of the truth anomalies of the topological operators generated by the higher form symmetries, and we are interested in the anomalies of these symmetries. And so my talk will be mostly about a microscopic point of view on these universal properties of the global symmetries. And we all know that the anyons can be non-abelian, hence generates non-invertible symmetries, but in my talk I'll be mostly focused on the invertible symmetries, and hopefully I can say something non-trivial about it. Okay, so let me get it started with a very simple example, which is already known. So this slide is completely a review. And so let's say we have some gapped local Hamiltonian system in 2+1 dimensions, and how do you define the self-statistics of the quasi-particle anyons in microscopic lattice models in 2+1 space-time dimensions. So such a procedure is known as a T-junction, which is a kind of classic paper by Levin and Wen. So they take some states with a quasi-particle. Actually, the configuration of the anyons doesn't matter. We can take some specific choice of we can pick some choice of the configuration of the excited states, and then we apply the sequence of the unitary operators. Each of them is an open string operator, which generates a symmetry and creates a pair of excitations. So these dots are abelian anyons, and each of the U hops the anyons and going back to the original one. So this, if you do the whole sequence, you go back to the original one. And this picks the Berry phase. And so each of them produces some local Berry phase, and the sum over this is thought as some invariance. And as you can see, intuitively, this process indeed does some half braiding of the identical particle. So you have some sense of this procedure actually does some half braiding of the anyons, hence produces some spin of the anyons. So you can just keep track of each of the anyons, and by doing this sequence of the unitaries one by one, you can see that it actually does a half braiding and get back to the original. Okay. But, well, this picture just doesn't imply that this is invariant. So in order to say it's invariant, we further need to check the stability against the possible local perturbations or the definition of the states or unitaries or anything. And this can be actually checked by the Levin-Wen paper. And so in my talk, I guess I'll be take it for granted. This is a very established fact. You could ask question about it in the question session. But so we can check that this is invariant on the choices of the unitary biphases or initial excitation configurations, or it is also invariant under the possible local perturbations, which can change the definition of the like excited states. So one question I can ask is that we, at the level of field theory, we know that the spin of the anyons is quantized over a specific root of unity, which is dictated by total quantum dimension. This is a general fact for the 2 plus 1 dimensional topological order. This is a statement about the modular tensor category known as the Buffer's theorem, that we know that like a spin of the anyons is quantized as a specific root of unity. So like we have to expect that for this microscopic version of the invariant for the spin, we expect that this is sort of the quantized invariant, which is a quantized root of unity. And so the question is that if this is really a quantized invariant. Okay. So this is actually a quantized invariant due to a funny reason. Let me explain with a specific, most simple example with a Z2 fusion rule, the abelian anyon with a Z2 fusion rule. Okay, so in this case, this like sequence of unitaries like decomposes into some local Berry phases. Each of the Berry phase is a function of the like excited configuration of the excitation together with some like a unitary I'm applying on this state. Okay, and then let's assume that each of the unitary is a finite depth circuit. So I'm not considering like a complicated QCA or anything. I'm mostly just assuming the like each of the symmetry generated by finite depth circuit. And then we can make one observation. The key observation is that suppose that we take a triple of the these symmetry, open symmetry operators, such that each of the 2 can have a non-trivial overlap. But if you take 3, you don't have like a mutual overlap, which is shared by all of the 3 operators. In this case, because I assume that like this is a finite depth circuit, if you take a commutator between them, like each of the unitary, the commutator of unitary support at like a mutual support of the 2 unitary operators. So if you further take like a triple commutators, like based on this choice of the unitary operators, this doesn't have any overlap. So this is just identity operator. So it does give you some trivial invariant, like given by some sequence of unitaries, and it gives rise to some specific combination of the local Berry phases, which becomes trivial. Okay, and then one observation we can make is that if you take 4 copies of this invariant, so if you take 4th power of this T-junction invariant, we can explicitly check that this invariance becomes like a combination, specific combination of the triple commutators as a function of this status, and this obviously becomes the trivial invariant, which means that this T-junction invariant with the Z2 abelian fusion rule is actually quantized as a 4th root of unity, which we all know from the field theory perspective. So it means that the microscopic definition of the spin has to be quantized as a semion or anti-semion or fermion. And we will see that such a mechanism for quantization is observed in a very general setup, like very generic dimensions and generic P-form symmetry. P can be 0 or 1 or anything. Okay. So any questions so far? Yeah.
So this is identity in the Lie group level, but suppose you translate onto the Lie algebra. This is a consequence of the Jacobi identity?
Sorry, well, what Lie algebra you have in mind in this setup?
Well, so you derive some identity for the spins.
Yeah.
And you're using first the commutator of, commutator equals 1, which turn into Lie algebra, would be just, some commutator of
you mean the algebra generated by these finite depth circuits, or like this?
Well, I think maybe let me ask the question differently.
Yeah.
Why this has to equal 1? This 4 combination has to be 1.
Well, it's because we assume that this is a finite depth circuit, so like each of them is arranged so that we don't have a mutual overlap between among these 3 operators. So this is according to the assumption of the finite depth circuit, this becomes identity operator. So that's why we get the identity.
It's not a very good answer, but it's okay.
Yeah, we can chat more. Yeah. Any other questions?
But if I consider an exchange on a larger set of the lattice, so you exchange by making a larger tour, you probably avoid this condition, no? So you define a minimal move in a kind of tetrahedron, but if I consider a move involving more spins, so larger, maybe you avoid this condition, no?
Well, like one can make a comment that this is stable against any possible local perturbation. So we could deform the configuration of the anions a little bit or locally create excitation. It is stable against any such perturbations. So that's one way to say that this is actually invariant under possible perturbation of the system. So I assume this is some topological quantity which is stable against any perturbations in the system. Okay, so before moving on to the generality, so let me also comment that we can also construct this kind of the invariance for the extended object as well. For instance, let's say we have we are in the 3+1 dimensional space-time where we have a Z2 one-form symmetry. It creates a loop-like excitation, which is considered as some it corresponds to, for instance, a magnetic flux in the 3+1 dimensional Z2 case theory, where the magnetic defects creates a generates a Z2 one-form symmetry. So in this case, it is known that we can compute the anomalies of the Z2 one-form symmetry in 3+1D, which is classified by Z2, and correspondingly we can find a single Z2 invariant. So this is given by the 24th step of the unitary operators. And we can actually check that this is an invariant, and this is quantized as a plus or minus one due to the same reason as I gave before, it's according to the higher commutators argument. And let me also comment that this non-trivial statistics given by this minus one invariant is called the fermionic loop excitation in the Z2 case theory, and this has been discussed in the Lyons paper in 2014, I think, and also a microscopic characterization of the fermionic loop statistics is not new. There was a prior very nice work by the Lucas and John Van Ha and Marshall Hastings, which characterizes the fermionic group by a 36 sequence of invariant, but we can shorten it. My collaborator kind of be able to shorten it by 12. It's kind of yeah. But so I can give a general framework for such invariants and discuss the physical consequences out of such invariants. Yeah. Anton.
Thank you. So the Z2 statistics of all excitations is imposed by requiring the unitary to square to 1, or?
I don't require the unitary to square to 1. I just require the excitations follows the same group algebra. So if I apply the unitaries on the open surface operator twice, it gets back to the original state up to a phase.
So it's a phase.
Yeah, phase can be arbitrary.
Okay,
so I just require the excitation follows the same group algebra.
So the condition then, okay, you act on the state with this unitary twice, you're going to get the same state up to a phase.
That's
okay.
right.
All right, thank you.
Yeah. Okay. Okay, so let me try to move to the generality. So, I want to construct this kind of invariance and say something dynamical about it. And so setup is that we have a local gapped Hamiltonian systems with a tensor productivity space, and we have a finite invertible P-form symmetry with a fusion group. P can be anything. So when P equals 0, G can also be allowed to become a non-abelian group, just a finite non-abelian group. And when P is equal or larger than 1, it is an abelian group. And we assume that this is generated by finite circuit. And actually, I don't refer to the Hamiltonian and just a reference to the state. So I can say this is actually emergent symmetry that preserves the state, not require the operator to commute with a Hamiltonian. So this is not an exact symmetry. This doesn't have to be exact symmetry. So in this case, the end of the symmetry operators corresponds to some excitations. And so in order to define the Berry phase, I need to set up the possible family of the excited states in order to discuss some family of the some paths through the family of the states to define the Berry phases. So this is I need to set the possible configuration of the excitations, which I define to be by kind of embedding some simple complex inside the space. This is embedded in the space, and then this we can talk about some a finite set of the excitations which is support at some simplices of this simple complex embedded in space. And then we also talk about the set of the symmetry operators, where the symmetry operators move back and forth the symmetry excitations configurations. For instance, if we talk about the T-junctions, this excitation configuration is the annual configuration of this simple complex embedded in the space, which can be regarded as some triangulation of the sphere. And then this S is some set of symmetry operators is just a line operator support at these edges. And then we want to define the Berry phase out of this kind of the sequence of unitaries go back to the original one. So this is generally given by the sum over the local Berry phases, which is a function of the excited states I'm applying on the unitary I'm applying. Okay, so this invariant, in order to set up the classification of the invariance, it's kind of convenient to introduce a formal sum of the objects, just regard this each theta local Berry phase as a sum, a formal object, and they consider the group of consider the integer direct sum of these local objects. And then this invariant is formulated as some specific subgroup of the free sum over this combination of the local Berry phases. Okay, so then so we can set a subgroup of the invariance as a subgroup of this free direct sum of these local Berry phases. And the detail is not important. I think I don't have a time to explain the detail, but just the important thing is that each of the necessary and sufficient conditions for being invariant can be compiled into the linear constraints on the integer coefficients that appears in the sum, that appears in the direct sum. So I can define the a subgroup of invariance which is generated by the integer vector satisfying all these constraints, and this is a subgroup of the invariance which is still free direct sum of z. So far there's no reason to be quantized, but so here's a non-trivial point that gives us to the quantization. So some of the invariance actually trivial, corresponds to trivial invariance, and this invariance originates from the higher commutators of the unitaries. So we have a set of so let's say we have a bunch of the finite diffs unitary circuits which generates a symmetry on the open surfaces, and let's say maybe part of them could have a mutual overlap, but if you take all of them, the common overlap shared by all of the symmetry operators is just a trivial. Then, according to the argument I gave in the previous slides, this just becomes an identity. So it corresponds to a trivial Berry phase. So we can define some trivial invariance, the group of the trivial invariance, or those generated by the higher commutators, and then we can define this quotient group where the higher commutators are factored out. And the non-trivial thing we can show is that this is a finite group. This is a finite group. Everything is torsion. So this is direct sum of the a finite abelian group. So because of that, we can actually see that this quotient group, like invariance in the quotient group is actually a torsion and becomes quantized invariance. So this is aligned with like a fact that all the anomalies of the higher form symmetries, for instance, given by torsion, a finite higher form symmetry is given by torsion, and this is aligned with the fact. Okay, so we can actually compute this kind of invariant on Mathematica, do the numerics research. So in order to do this, let me specify the a possible excitation configuration to be some canonical choice of the triangulation. I just take to be a minimal triangulation of the sphere, and then we consider some extended excitation, possible configuration of the extended excitation of this triangulation, triangulation of the sphere, and then there exists some systematic algorithm to compute this invariance out of the input of this simplicial complex and together with a fusion group. This uses some a matrix, some technique of the integer matrices defined out of the higher commutators. It's kind of neat, but I don't explain it. Then the computation results imply the exact correspondence with the group cohomology of the Eilenberg-Markov spaces, which can be verified for the small groups. And for instance, in the case of the two space dimensions, in the one-form symmetries, where we have, this is just anyons. In this case, it is known that the spin of the anyons is quantized as like a 2n roots of unity for the even n, and the nth root of unity for the odd n. And we can derive this kind of a Pontryagin square periodicity up to n equals to 10, for example. So these are kind of the examples of invariant we can find with the numerics. So this is a Fermi group excitation. Some of them are known. Sorry for the not putting the references. This is definitely known. But for instance, in the case of the 3 plus 1 dimensional Zn symmetry, we have this group cocycle that generates anomalies. This kind of sequence of invariants captures the anomalies of the zero-form symmetries. So let me, in the remaining time, let me mention the, okay.
Can you do also non-abelian groups?
Yeah, we can do the non-abelian groups. In the case of zero-form symmetries, it's definitely doable. Yeah, we can check for the, for instance, S3 symmetry, which is found in the paper. Yeah.
Because you talked about the group cohomology, no?
Yeah.
Can you also detect some discrete gravitational anomalies with this method, or no?
No, this is just a group cohomology. Okay. So, yeah, everything would have to be. Yeah, but well, some of the group cohomology anomaly will be understood as mixed gravitational anomalies, due to the evaluation or something. Yeah, but we can't do the pure gravitation.
Okay, but you know it's impossible.
Yeah.
Okay. No, thanks.
Let me mention the relationship to the anomalies. So this kind of non-trivial invariance, given by the sequence of unitary operators, is kind of directly regarded as obstruction to Gaussian symmetry. Let me explain why. A take is that this product of unitaries is sort of regarded as a product of the Gauss operators. So let's say we have some a product of the symmetry operators, and if you can turn on the background gauge fields, if you can turn on this gauge fields, we can express each of the symmetry operators on the open surface as some product of the Gauss operators. And then this is essentially evaluating the product of Gauss operators on the with reference to the some specific symmetric state. And having this kind of non-trivial invariance basically means that there is an obstruction to the commuting Gauss operators within this state. So it basically means that the invariance obstructs the commuting Gauss law, and there's no way to gauge the symmetry. So I take this to be the microscopic definition of the truth anomaly with reference to this state. And then I'll talk about people like the truth anomalies because there is a dynamical consequences. So we can actually directly show the dynamical consequences for given invariance. So let's say we have some symmetric state where we can define this kind of invariance. And then generalized statistics, like this non-trivial invariant on the symmetric states directly implies that the state cannot be a short-range entangled state. So it means that we cannot connect the state into the trivial product state by a finite circuit. Like for instance, if you have a 3 plus 1 dimensional state with Z2 form symmetry, if you observe that this is a non-trivial invariant, like this Feynman group statistics is -1 on the state, it means that it cannot be short-range entangled states preserving the one-form symmetry. So this is the long-range entangled states. So let me mention that such a result has been known for the 2 plus 1 dimensional anion statistics, and the microscopic definition of the self-statistics of anion is shown to the like enforced long-range entangled nature, which was originally shown by the Bravey Hastings and Frank Strate. And see also recent discussion by Benny Yoshida's paper. And so this is one of the dynamical consequences, which is very familiar from the like a usual anomaly matching, where anomalies implies a no trivial gap phase with preserving symmetry. But in the case of the higher form symmetry, we can say something more tight on the entanglement structure of the states. So suppose that we have a P-form symmetry where the P is equal or larger than 1. So here I don't consider 0 form symmetry. Then if you have a non-trivial anomaly captured by this invariance, then this overlap with this state with any choice of the short-range entangled states has to decay faster than any polynomial of the system size. So this is kind of pretty intuitive from the theoretical point of view, because spontaneous breaking of the 0 form symmetry can imply the cat state, symmetric cat state, which has generally has a finite overlap with the short-range entangled states. But in the case of the higher form symmetry, its breaking, spontaneous breaking means that the topological order phases, and it generally requires some linear depth circuit to prepare it. So I would say the higher form symmetry, anomaly of the higher form symmetry requires more, like a much more like a long-range entanglement compared with the 0 form symmetry. So this constraint is only valid for the higher form symmetry, and in the case of the higher form symmetry, we can make this kind of argument. And this kind of the constraints on the entanglement structure is recently used in the context of the mixed state topological phases, where we generally have some mixed state subject to the decoherence, and if you enforce some specific form of the symmetry of the density matrix, then like it leads to the non-trivial entanglement structure of the mixed spaces of matter. Due to the time constraint, I guess I don't explain detail, but basically we can say that if you have a strong anomalous higher form symmetries dictated by this invariance, then we can directly show that any fidelity between the mixed states and any choice of the short-range entanglement, short-range entangled state has to decay any faster than any polynomials. And it leads to some interesting mixed state topological phases, such as for instance, we can consider the 3 plus 1 dimensional Z2 toric subject to some funny decoherence. This is arranged so that we preserve the specific Z2 one-form symmetry, which is anomalous. This generates some Feynman group excitations. And deep in the decohered phase, it's experienced some coding tradition, and it has some decohered phase. But even in the deep decohered phase, we have a non-trivial, we have an anomalous one-form symmetry which is preserved strongly, and then it means that the intrinsic long-range entanglement, in the sense that the fidelity between any choice of the short-range entanglement has to decay exponentially and leads to some mixed topological phases of matter. So this is joint work with Porsche and Abhinav. Okay, so let me summarize my talk. So I offered some universal microscopic description for the statistics or anomalies of the high-form symmetries or zero-form symmetries, which can be non-abelian. And this is a quantized invariant, and it generally gives rise to the invariant definition of the anomalies in the microscopic lattice models. And it constrains the low energy spectrum, so we can say pretty generally the dynamical consequence of the anomalies. And if you consider the higher form anomalies, it enforces the intrinsic long-range entanglement in the sense that the overlap with any choice of the short-range entanglement short-range entangled state has to decay faster than any polynomials, and it leads to the new mixed phases of the topological, new mixed topological phases of matter. Okay, that's what I want to say. Thank you for listening.
All right, very interesting talk. So I have two comments, one question. So first about this T-junction defining statistic. So when I said it's not a good answer, I was expecting you to say the following. So we have 4 anyons on the sphere. And then they should get a representation of the mapping class for the 4th sphere, which is SO2Z. And then if you just apply this to some kind of identity, you should get probably the spin quantized. So I'm expecting you to say, oh, this is derived from some kind of identity.
Yeah, well, it might be possible that this kind of mapping transformation will be associated with some maybe unitary transformation.
Yeah, that's why I'm
yeah, that's an interesting observation.
So the second comment is you said generalized statistics given by a group cohomology.
That's a conjecture.
Probably you need to change a little bit. So in 2 plus 1 dimension, we know abelian statistics are given by a quadratic form. That's not the standard group cohomology. That's called abelian cohomology.
I meant the group cohomology of Eilenberg-Markov space. So this includes a group cohomology of
okay, you have to change to abelian cohomology.
It actually dictates it actually includes a Pontryagin square.
Okay,
okay.
So that's called abelian cohomology, not a group cohomology. Okay, so the question is for 3 plus 1 dimension diagram for Witten theory. Can you define the statistic for loop excitations?
Yeah, that's right.
How do you do it if you can?
Well, one thing we can say is that even in just a Z2 toric code, like a Z2 gauge theory with a bosonic quasi particle, I can find a non-trivial loop-like excitation, which is an integral of B plus A cap A. This is anomalous Z2 one-form symmetry, and it has a non-trivial Z2 invariance, which is shown by these 24-step unitaries. So we can find this kind of examples. It's kind of interesting.
I have a question about some remark you made about relation with anomalies and statistics. It's a bit confusing because statistics usually think about properties of excitation of a particular state, while anomalies are usually just about an action of a symmetry on some lattices. For example, if you go to 1 dimension,
so
your particles would be like statistics in quotes would be some degree 3 cohomology class of the group, right?
Yeah, I agree. So,
but that's nothing to do with the states. It's just
no, you're not mistaken. The unsatisfying, this is just unsatisfying thing about our work. So we need to make an explicit reference to the state to define this kind of invariance. But as you say, anomaly is a property of the state. Property of the symmetry instead of the state. So we should, for instance, I forgot to mention because there's another very nice work by Elsnayak or also Sahans. They have an alternative characterization of the anomalies, which doesn't make any reference to the state.
So it's just an artifact of how you present things. So you can also reformulate all this without mentioning the state. That's using the comment. For example, you define some relations using expectation values in a state, right?
Right.
But in reality, the commutator literally could be, let's say, declared to be like 1, some higher commutator, right? You could define just your group by saying, well, I impose a relation that the commutator, some higher commutator is just identity.
Yeah.
This would be the same, give you the same result. You don't have to mention state. Is it correct?
Well, I need to think a bit carefully, but in order to I'm not really sure if I can forget anything about the state. What I can say is that the invariant is independent of any choice of the excitations, as long as I have some canonical choice of the gapped state with exponential decaying tails, exponential decaying correlation lengths, so that I can say something about a stability against local perturbations. But for instance, in the gapless spaces, I'm not really sure yet if it can be promoted by really a statement about the symmetries. It will be interesting.
I'm just wondering, Nyack-Nelson computation doesn't make reference to a state.
Yeah, right.
What you're saying, is it equivalent to yours or just similar?
Well, well, in some sense, it's worse than the Nyack, but this is. So Nyack is about zero-form symmetries,
right?
And it doesn't make a reference to the state as.
So it's similar, but not. It's not a special. Their result is not a special case of yours. Is it correct?
It's not a special case of ours.
Okay.
Yeah. So I can extract the anomaly. I can characterize the anomalies by some invariant, which is some combination of some group cocycle, which is a partition function of the SPT phase on the cross manifold. But meanwhile, the Nyack was a Hans paper extract some single group cochain, single group cocycle for the anomalies. So it's a bit different.
Okay.
Yeah.
So thanks for the talk. So recently there is a conjecture on the higher form symmetry anomaly and the multi-part entanglement. So could your framework also prove that?
Well, so far I've only been able to say something about the bipartite Lagrangian entanglement. Yeah. So this is purely a statement about bipartite entanglement. I haven't been able to say anything about multi-party entanglement. Yeah. But I know that some Chong-Wan's interesting papers which says a multi-patent entanglement, obstruction to multi-patent decomposition, using the Nyack's characterization of zero-form symmetries. It will be very interesting to generalize this kind of statement to the maybe higher form anomalies. But in order to do this, I guess we need to really talk about a generalization of the Nyack to the higher form symmetries.
Thanks.
So there are some examples of systems that feel like they might be a counterexample to your argument for quantization. So I wanted to sort of see, well, let me tell you what the example is, and I'm curious what you think about it. So these are systems in 3+1 dimensions that are described using infinite component U1 Chern-Simons theories. So you can think about them as layered systems. And this is all coming from a paper by Xie Chen and collaborators. You can think about them as layered systems where all the excitations are moving in parallel planes. So that the excitations have irrational topological spin, and they also have irrational mutual statistics that decays exponentially as you increase the transverse separation between excitations. It seems like, but statistics can be defined, at least in principle, I think, using the same kind of T-junction for these excitations, right? The geometry that goes into the statistics is really the same as in 2D. So I'm wondering, is this a counterexample? Because certainly the string operators that move the excitations will definitely be very fat. They'll have to have very big tails, extending transverse to the string direction, because otherwise you couldn't have this exponentially decaying mutual statistics. But I guess what I don't see what the fundamental difference is between those string operators and string operators in a 2D chiral states, where we think the statistics should be quantized, but the string operators are also kind of fat.
Well, my take is that if spin is not quantized by rational numbers, it would mean that it's not really a gapped phase with a infinitely degenerate ground state. No, then I'm not sure if my argument really works. I really consider gapped phase with exponentially decaying correlation functions. Well,
but these are definitely gapped with exponentially decaying correlation functions.
Oh, really? Then, well, I'm not really sure. Yeah, we can chat more about it. I need to understand the detailed systems. Yeah, thanks.
For finite system size, it's always rational. It's just that when you take the limit, it becomes irrational. It's just like a continued fraction, and then in the infinite limit, it becomes irrational.
Yeah, but we should always work with the limit. So yeah, okay. So my comment to Nat's observation is that we should always work in the thermodynamic limit. Like, I don't see why the argument doesn't apply. So I would agree with that as a resolution. Like, if somehow you needed to be in 2+1D to run the argument, but you don't. You can run this argument in 3+1D. So I don't think that's the resolution.
Like, well, I'm not sure, like, this, because this characterization of the microscopic statistics is kind of mesoscopic quantity. Like, you can just focus on the subsystem. Like, and we can just define the sequence of unitary operators, and they don't really care about the thermodynamic limit or anything. Yeah, I'm not sure what is happening.
Perhaps resolution is simply that you assume that there's a finite number of superselection sectors governed by some group, finite group, while in this setup that Mike say, supposing there is infinite number of them. So you, yeah. Okay, maybe that's okay. Yeah. So okay.
I see. Yeah, that sounds right.
Yeah, that might be the resolution, because the fusion group in that case actually has infinite order elements. Which is why you can have the irrational statistics at all.
That sounds reasonable.
You mentioned a generalization to gapless systems. In that case, would you want to have these string operators extend beyond the correlation length?
Well, I guess I still want to assume that this excitation is still gapped. For instance, there's some physics notation, we have a gapless spin leakage where the phases are still characterized by the bosonic or fermionic plus a particle of the E1 spin leakage. I guess we still need to ensure that the excitations are gapped. And as long as the excitation is gapped, I guess we can say something, but I haven't been able to establish it.
I see. Do you think there's a way to define some kind of statistics for gapless excitations as well?
Oh, that I'm not sure. In that case, maybe it's no longer associated with anomaly of the generalized symmetries, right? And in that case, I'm not sure if you can say anything clean. But it's an interesting question.
Yeah, we have time for some other quick question. Okay, if not, let's thank Ryohei again.